Dear all, welcome to today's Svein Rosseland lecture. Svein Rosseland was born on the 31st of March in 1894, and he passed away on the 19th of January 1985. After a humble start, he in 1920 received a fellowship to study with Niels Bohr in Copenhagen. During the next few years in Copenhagen and at Mount Wilson Observatory in California, he made several theoretical breakthroughs, applying the latest findings of modern physics to astronomical problems. Most famous is perhaps what is called the Rosseland mean opacity. In 1928, at the age of 34, Svein Rosseland was appointed to the professorship of astronomy at the University of Oslo and the directorship of the Oslo University Observatory. With strong economic support from the Rockefeller Foundation, the Oslo University Observatory was in 1934 closed and astronomy reopened in a new building at the new Blindern campus as the Institute of Theoretical Astrophysics. Svein Rosseland retired from his professorship and from being head of the institute in 1965. At the 100th anniversary of Rosseland's birth in 1994, we started a series of annual Rosseland lectures to honor his memory. We have had many of the world's most famous astrophysicists giving the Rosseland lecture. This year, we are especially lucky to be able to introduce to you Professor Conny Aerts. Conny Aerts is professor at the Institute of Astronomy, KU Leuven in Belgium, where she also received her PhD in 1993. Besides her professorship at KU Leuven, she leads the chair in Asteroseismology at the Radboud University, Nijmegen in the Netherlands, and she's external scientific member of the Max Planck Society in Germany. Professor Aerts is one of the leading pioneers in asteroseismology, and she received the Kavli Prize of Astrophysics here in Oslo in 2022. When she received the prize, the Kavli Astrophysics Committee wrote, "Her remarkable involvement in observational approaches to asteroseismology, both from the ground and from space, using data from Corot, Kepler and TESS, has had a very strong impact. Aerts is widely known for her work on massive hot stars, extending the impact of asteroseismology across the Hertzsprung-Russell diagram. She is a leader in probing the interaction between pulsation, rotation, and stellar winds through an integrated approach, taking advantage of changing spectral line shapes as well as photometric variations. In particular, she developed clever methods to identify pulsation modes in massive stars, opening the door to the modeling of their interiors. Aerts also pioneered a rigorous methodology to identify and model gravito-inertial modes in rapidly rotating stars, allowing estimates of rotation and mixing in stars with masses between 1.3 and 40 solar masses. Thus, her work has enabled the first quantitative estimates of near-core and envelope mixing, leading to significant improvements in stellar evolution theory." So now we are really excited to hear Professor Conny Aerts on novelties in stellar evolution, asteroseismology of fast rotators.
Thanks a lot, Per, for this very kind introduction. It's great to be back here in Oslo, where I was treated so well 1.5 years ago. This was the best week scientifically of my life, for sure. So it's a pleasure to be back and to even have a representative of the Flemish government here, of which I'm very proud. But I will mainly address the youngsters in the audience who come here to learn about astroseismology, let's say. Okay, let's keep going. If there is one message that I want to give you and that I want you to take home from this lecture, is that waves are fantastic. Waves allow us to see what is not visible. And so I hope to convey that message to you throughout my talk, and also about some methods where we can use this saying. You know about that. Medical doctors, for instance, know about that. Huh? We take ultrasound. Well, they do, not me, because I'm not an expert in that. But they take ultrasounds to find out what's going on in the human body. a bit more close analogy to what I do is earthquakes. And you see here a seismographic measurement where earthquakes create waves, and they allow geophysicists to find out what is happening deep here inside our planet in terms of chemistry and physics. And I just do the same, but then for stars. Now, stars are gaseous spheres, so they are not crusty planets like the Earth is. And luckily for us, earthquakes create waves, but they are a very local phenomenon, luckily for us human beings. And not so nice phenomenon, except for the geophysicists who use the waves created during earthquakes. In a star, it's a little bit different. A star is a hot gaseous sphere, and it moves up and down globally as a whole in a complex way, but the waves created can be analyzed in a very similar way. So geophysics and astrophysics actually, for that reason, go hand in hand. It's just that the spherical body is a bit different, and the oscillations are global in the case of stars, okay? Nevertheless, we can use the same technique. And here I brought a star that you see in the upper diagram, whose brightness effectively changes as a function of time. So you see this blue seismographic measurement, very much in analogy to what the seismographic measurement of an earthquake is, but now for a very distant star in our galaxy. And you see the variations indicated in the light of the star expressed in part per thousand, promille if you like. That's the term we know also from other human activities. So you see there is a lot of seismic activity in this particular star. I've plotted it for 15 days, but in reality this measurement takes 1,500 days. This star is observed by the Kepler satellite, funded and developed by NASA, and it has observed stars in one position in the northern hemisphere, 200,000 stars, during 4 years uninterruptedly. And so these type of measurements really allow us to study the waves that are created by this up and down motion of many, many oscillations in this star. Now, how does it actually work? I often get the question, why are you using the term asteroseismology? It comes from Greek. It's about seismic activity of stars. Aster, seismos, and then logos is what we are doing by the day. We make some kind of reasoning or exploit the information that the waves give us in terms of physics and chemistry. And so you can see that here in this graph, indicated as ray paths. So waves inside the star where you can't look, they propagate and four are drawn here in different colors. So the red wave is sort of probing this outer layer, and the blue wave goes completely through the star. That's my favorite types of waves, because the life of the star is very much directed in its very inner regions. And so it's important that we can probe that. And then you have this green and yellowish wave that bounces in certain regions, as you see here. And so the trick of astroseismology is to try and observe these types of waves from the measurements that I showed in the previous graph, and then to make the following reasoning, like this yellow wave here probes a certain region, the green one too, and the green waves go a little bit deeper inside the star than the yellow waves. So by subtracting the frequencies of the green and the yellow wave, we have actually a measurement that can be connected to the physics of the layer that is green here but not yellow. And so if we have many of these waves, then we can reconstruct the physics of the star layer by layer. And that's the trick. That's the analogy to sort of the ultrasound, you could say. Okay? That's how we see the invisible. Now, where can we do this? Well, nowadays we use space missions to do this science, and we are lucky enough that we can do that for many stars in our galaxy. This is still a scientific case that is very close to us. It's our backyard, so to speak. So it's not far away in the distant universe, No, it's relatively close by. Why? Because we need to have a detection capacity for tiny little brightness variations. And the star I showed in the beginning had parts per 1,000, so it means you see changes at that level, but some only have parts per million, like the sun has, actually, when it has its oscillations. You can't see that by your own eyes. Your eyes are beautiful detectors, but not strong enough to see the solar oscillations at the surface. But of course, we can resolve the sun in the sky, so it has an advantage. So in brief, we can do this type of science fairly close to us in terms of cosmological standards, okay? Now, the galaxy has billions of stars, and many of them have oscillations, but not all, right? The range in masses where we can do this type of science is indicated here. So for stars that have about only 0.7 times, so a bit less mass than the sun, all the way up to stars that are 25 times heavier than the sun. And so the sun is indicated here as a star in sort of the lower mass regime, yeah? And what you need to realize is that the more mass a star gets when it's born, the faster it dies, the shorter it lives. But the more important it is for the chemistry of the universe. So these stars here, these low mass stars, they live very slowly. And in fact, the ones in our galaxy were born shortly after the Big Bang. So these stars are still in their early childhood. As I call them the children of the universe. Right? And they are metal poor, because in the beginning of the Big Bang, there was only mainly hydrogen, helium, and a tiny little bit of lithium, and all the rest is created by stars, including the material that we are made of. Right? That is created mostly by these very big, massive stars, blue stars. They are hot, and they live very shortly. In astronomical terms, this means several million years, which is very, very short. Yeah? Here, it's billions and billions of years. Okay? So very many generations of these big blue stars have already passed in our galaxy and have given their material that they have created in their interior back to the galaxy where new generations of stars are formed. Now, we know more or less how this works, but the devil is in the details, I always say. There are still quite some unknowns that we don't know yet, and that's what the purpose is of astroseismology, to improve stellar structure and evolution theory. Right. Now, another difference that's indicated here is that stars on this side are very slow rotators, including our sun. Our sun takes about 26 days to revolve around its rotation axis. Right? These stars are very fast rotators, some even so fast that we have them rotating at what we call almost critical rotation. What does that mean? If you rotate, well, then there's a centrifugal force. Yeah? And when that force is so big that it overcomes gravity that keeps the star together, everything flies away, and you can't have a star anymore. And so these big blue stars, they rotate fast, they live a short lifetime, they do a lot of production of chemical elements, and then they explode as a supernova. Right? Now, the key difference in this storyline is that the position inside these stars in terms of energy that they create in their nuclear fusion gets transported inside the star in a very different way in such a light star compared to a massive star. And that's indicated schematically here by these signs like these circles. These are convective motions, so that's turbulence that is happening in stars, boiling gas, I call it, right? While in other parts, like in the sun, for instance, the transport of the energy is being done in a radiative way, so by photons that find their way towards the outer layers. And so this makes a big difference in the life of the star, because if you have boiling bubbles, then all the material is mixed all the time, right? While if you have a radiative energy transport, then it's nicely, slowly diffused, and you don't mix your materials so much. So we know that there is a difference inside stars, blue ones compared to the very red ones, high mass stars, low mass stars. But we don't know exactly where the transition of these convective turbulent layers versus these radiative layers, where they are located. And this is where waves come in, because they tell us where they are located in a way that you can't deduce from simply looking only at the outer layers of the star. So the waves are really important to determine these transition layers. Right? Now, here are some oscillations of stars that are color-coded in blue and red. So this is for a massive star. So you have to imagine here is that turbulent core of a massive star, and then the radiative zone, and at its surface and in the interior, the gas is moving up and down with different periodicities and with a different amplitude, a different strength. And so we, astroseismologists, cannot see this directly. These are animations. These are not real stars. But it's to give you a flavor of how these non-radial oscillations of stars look like. So what you actually do is if a star would not oscillate, it would be a sphere, would be boring, it would be a completely white in the animation, but the oscillations make it move up and down. And when it moves up, the matter comes to you as an observer. So then it's blue shifted. When it goes down inside the star, the matter is going away from you and is red shifted. That's why the color coding is used. And so what we astroseismologists have to try and do is unravel the light curves that I showed in the beginning and couple it to this type of mathematical functions. That's not so easy, and that's why it took us a long time to develop this field, okay? But nowadays, we can do it. And, you know, since I went a bit too fast, since I'm in Oslo here, a tiny little bit of mathematics for the waves. The sun is a very much appreciated object here, and the sun really paved the way of this research domain. So here, for the mathematicians among you, and also the physicists, of course, here's the wave equation. This is just a symbolic write-down of an equation that mathematicians love to solve, right? And the solution of this equation is actually the displacement, these red and blue patches that you saw, at the stellar surface, right? And so it goes like one of these spherical harmonic functions, yeah? And it has a time dependence, a frequency. So our task is to unravel that. And so let me simplify this for those who are not familiar with that type of mathematical formula. Don't worry, I will not bring back other mathematical equations. I'll just show you how it works. The variability of the brightness, let's say there is one stellar oscillation, one starquake, if you like, with a certain periodicity, and this is expressed in days. So between 0 and 0.2 days, that's about 5 hours, right? Yeah. Now, what do? Seismologists, we don't look only at the brightness, but we love to put this in our brain and in our computers in Fourier space. So if you Fourier transform this sine wave that's periodic, you get one peak in the frequency domain. Engineers do that all the time because they need to know the vibrational frequencies of a bridge when they build it to make sure it can't collapse, right, when it gets perturbed. Well, I perturb stars. Well, I don't do it. They do it themselves. And so I need to know the eigenfrequencies of these stars, right? And here you see one peak appearing because of this periodic variability of about 5 cycles per day, okay? Now, we don't have just one sign. No, we have a whole bunch of them. This is the same star I showed in the beginning, yeah? So the measurement is a quite complex sum of sine functions that each have their own frequency. And that is what we want, because the wave frequency is really determined by the internal physics. So we Fourier transform this, And here you have the amplitude of the oscillations as a function of frequency, and each and every black bar, you could call it, is a wave frequency. And so as soon as we can measure these frequencies, we can do seismology, provided that for each of these, we can find out what the spherical harmonic function is that is connected to this time dependence. And that's the tricky, difficult part. Huh? So mode identification, as we call it, has to be done for each of the observed signals, for each of the observed frequencies. We have to try and find out what the picture is, what the spherical harmonic function is that belongs to it, without being able to resolve the star. Huh? Stars are just tiny little dots, okay? And so in order to do seismology, that is to say we have the observed changes in brightness that come from the surface, but what we actually want to do as seismologists is dive deep. I'm making you dive deep into the star symbolically to find out the physical circumstances here, right? So we have to do a measurement of the frequencies of the waves, and we have to label them with the correct spherical harmonic function, okay? Now, how do we do that? Well, we use the sun as an example. Before I go into that, what is dominant in the character of these waves? That's the force that is bringing the displacements back into equilibrium, right? And so there are mainly 5 forces that I want to mention here, and each of them creates its own type of waves. So you have a star is a gaseous sphere, a hot gaseous sphere, that you perturb, you move it up and down. Each oscillation does that. And if you put a gas that is hot deeper together, or if you expand it, you create sound waves. I'm doing it right now in this room for you, and that's why you can hear me, okay? So you're quite familiar, I think, with sound waves. Even if you're not in the sciences, you know how to interpret them, right? On the other hand, if gravity or buoyancy is the dominant restoring force, that's when we speak of gravity waves. Yeah? And these waves, they probe really the interior of the star. That's the purple wave that I had indicated in my beginning slides. Another thing that you know, I think, from experiments, if you walk on a merry-go-round, for instance, if rotation is occurring, you have a Coriolis force. That's the same force that makes your water in your bathtub rotate differently in the northern and in the southern hemisphere. The Coriolis force, when that's the dominant restoring force, you create what we call inertial waves. They are happening right now in this planet, whether you like it or not. We are rotating, and we have a Coriolis force active in our planet, and that creates inertial waves in the deep core of the Earth. Rotation inside stars creates inertial waves in stars. How can we unravel them or try to understand them? Well, then we need to know how the stellar gas is rotating around an axis. This is very hard to do because we can see that for the sun from its outer layers, but that doesn't mean that the rotation that the sun has at its surface, 26 days more or less, doesn't mean that it does the same periodicity in its interior layers. So this is something that we knew very little about until about 10 years ago. And then some stars, not all, have strong magnetic fields, so there is also a Lorentz force. And that creates Alfvén waves, as we call them, so another type. And then some stars happen to be with 2. We call that binary stars. And as you know very well from the Earth-Moon system, that creates tidal forces. If the tides are the dominant restoring forces of the waves, we create tidal waves. So there is a whole bunch of waves that we must study. And in fact, there are whole communities for each and every restoring force has their own experts in the field. So it's quite complicated because these waves, they don't interact separately. All these phenomena, they are acting together because there is gas pressure in a star, there is buoyancy for sure, because the gravity force is active. Stars rotate, so they are, also subject to a Coriolis force, whether we like it or not, etc. So in practice, these types of waves, they get mixed, as we call it, mixed character, okay? All right, let's see. So here's an axis with my equation. Don't worry about the equation, but here I have drawn a very simple frequency axis. So each wave is somewhere along this axis with a frequency. For the sun, the acoustic waves are at high frequency. They are, typical for acoustic modes, right? A few minutes, as I will show in a minute. My stars, well, nobody owns stars, but the ones that I favor sit in this part. And then all these forces that I've just discussed, they all interact with each other. And there they create slow waves. So here the waves are fast, here the waves are slow. Okay. These are easy. You can ignore that there is rotation, for instance. These are not so easy. Yeah. And so that's why our field very much got kick-started here, also thanks to the sun and successors of the sun, let's say. Okay? Now, how do we do our daily work, so to speak? Well, we have beautiful observations nowadays brought to us by space missions. You have seen this signal now already several times. We measure the frequencies. We try to label the way it goes up and down in terms of these red-blue patches. And so we have observed and identified oscillation modes. Right? That's the observational part. Instruments are being built, are being calibrated, and are being used by observational astronomers. Then we have a left part that is a bit more complex. Let me take you through it. We have a theory of how stars live their life, right? Of how they are built, how they are structured. Right? This depends on their mass, as I've explained in the beginning, and the mass tightly couples to how long the star lives. It's also connected to the chemical composition, so the material it got at birth, and then it evolves. Yeah? What we do is we have computer models mimicking the structure and the life of stars. These stellar models solve these nice complex differential equations. And then, when we have a star, it's being perturbed. It's being displaced for each oscillation mode, right? So we compute what we expect theoretically to be the starquakes for each model, right? These are the theoretical predictions, and of course we compare them. And then we notice, oh, this is not a good match. What do? Well, we realize our models aren't great. So we have to change the physics and the ingredients in our models. We again compute the model. We predict the oscillations. We hope that we are closer to reality, and we bike through this diagram a whole lot of times until we come close. Now, the most precious unknowns here are actually this convective motion, the rotation that is happening in the interior of the star, as I said, and also the way the material mixes. If you rotate faster, then you mix your material way more efficiently. You know that maybe from the coffee that you took just before the lecture, right? If you put milk in it, certainly, I don't know if there were spoons. Yes, there were spoons, of course. You took a spoon, why? To mix the coffee and the milk a bit more effectively than if you were to have no spoon, because it would take a long time before that milk and coffee would be merged, and then the coffee is cold and it's not nice, okay? So gaseous spheres, stars that rotate, they are much better mixed. It's the same phenomenon, except that coffee is a fluid, and the star is a gas. So knowing the rotation of a star is critical to understand the chemical mixing. Okay? Now, the first attempts that I tried in this field, I'm still proud of that, is for this star. What you see here, you see measurements, about 1,500 measurements. It was long before we had satellites doing this. So each and every dot in this plot, it took me going to the telescope, putting the star in the diaphragm, measuring the brightness, and do that throughout the night, right? So this was not started by me. In fact, it was my supervisor who already started observing this star. In 1983, then I was still in the studying mathematics. Huh? And so it took us 20 years, as you can see here, to understand 6 oscillations of this star. And you see them here indicated as black bars in the Fourier transform. Now, I was able to label these from the rotation that shift these frequencies that you would otherwise not see as 3 measurements. So here you have 3 oscillations because there is an interaction between rotation and up and down motion of 1 oscillation mode. Yeah. So if the star were not to rotate, it would be 1 bar here, not 3. We call that rotational splitting. And it took us a long time because you have to resolve these frequencies. You have to unravel that there are 3 and not 1. And from the ground, that's very difficult. Because if you have to go every night to your telescope, well, you have to observe that. And then there's the night, and then there's rain, and then there's technical problems, and etc. And then the Earth atmosphere is bothering the measurements. So it took really a long time. Now we do this type of science very differently. So 1 star, it took me in my early PhD and postdoc career, took 20 years. That's not a very good prospect if you have a career as an astronomer, right? You can maybe do 1.5 or 2 stars. I mean, that's a no-go. Now we do that with machine learning. And so I'm not going into details, but we have space missions like Kepler and TESS. TESS is working right now still. They do millions of stars now, literally true for TESS, right? And we have a whole battery of machine learning software people who unravel these oscillations and put all these stars in variability classes. So rather than 1 star on 20 years, we do now a few years and millions of stars. You see the big boom in this field, right? Now let's go back to the sun. The sun taught us how it works. Huh? The sun here has the solar oscillations plotted as a function of frequency. The dominant one is about 3,000 microhertz. That's 5 minutes. The dominant solar quakes go up and down in 5 minutes, and there are many. And so these are sound waves. It's a slow rotator. If you go up and down in 5 minutes, then you basically can say, well, I know there is rotation at the sun surface, but it takes 26 days. 5 minutes divided by 26 days, that's the Coriolis effect. That's very, very small. You can ignore it, okay? The same is true for the magnetism. The sun has a magnetic field with spectacular phenomena that people here in Oslo know much more about than me, but it's a relatively low effect of the Lorentz force, so you can also ignore it, right? And so from these patterns, you can actually deduce the mean density of the sun, and mainly its size. Now, of course, we know how big the sun is because we can measure it in the sky and we know how far it is. But the dominant frequency here tells us, since it's a density measurement, we know the mass. That means we can deduce the radius. And we can do that with a very high precision, right? Only a very few % uncertainty, right? So that's great. We can do that for the sun, and here is a copy of the sun, that's 16 Cygnus. It's a star that from the outside is a copy of the sun. A seismologist immediately knows that this is wrong as a statement, right? Why? Because the dominant, again, beautiful oscillations, huh? It's similar to the sun, but the dominant frequency here sits between 2,100 and 2,200 microhertz. The sun had 3,000. The sun was somewhere there. If the frequency is higher than this star, lower frequency, it means that the sound waves need a longer time to travel through the object. It must be a bigger star. It's as simple as that. It's like musicians know this very well when they produce sound waves. Okay? So this star, from this peak, we know it's a bigger star. And if the star is bigger, then we can deduce from our knowledge of how stars live that it's an older star, somewhat older, but still fairly similar to the sun. Okay? Now, why is this important? Because we can apply this to stellar oscillations of stars that also host planets. So people who study exoplanets find it magnificent, and here is a plot of that made by Ashley. She's a PhD student, and whenever I use a plot that's not in the literature, I put a picture as a courtesy to the person who made it. Here you see many, many exoplanet hosts. The sun is an exoplanet host, right? And the colored symbols are stars where the host star of the exoplanetary system has oscillations that have been analyzed by astroseismologists. And the nice thing about that is, how do we come to find these stars? Well, from planetary transits. So here's your star, a planet comes in front, and so there is a dip in the brightness variation. That dip is very small, and you need a high precision to measure it. Exactly the same precision than my starquakes, right? And so by measuring this dip, you know how big the planet is, conditional to the fact that you know how big the star is. But you can't resolve the star. We don't see this in practice. We only see this dip in the data, right? But if you know the stellar radius, then you can deduce from this dip and from the duration of the transit how big the planet is. And that's very important for exoplanetary studies, right? And of course, we know how big the star is if we have seismology. We can measure it up to a % precision. So astroseismology delivers input that's very important for exoplanetary studies, including the ages of stars, right? Now, you see that here in practice. These are red giants. This is what the sun will become when it's old, when it's about to die. Yeah? And you see how many stars? 7-ish, huh? Observed, again, by the Kepler satellite. The black are the frequencies of oscillations, and you see them going from about like 250 microhertz all the way up to like, say, 20 microhertz. The sun had 3,000, so this is a way, way bigger star because the frequency is way, way lower, 10 times as low, okay? This is what the sun will do when it's about to end its life. It will become 10 times bigger. We call that a red giant. And this one is younger than that one, and that one, and that one. Why? As the star grows old, it gets bigger and bigger and bigger and bigger. This takes millions of years. But by stacking this for different stars, we can see that in practice, okay? Now, we can do that for all the stars in the galaxy, and this was actually pioneered by the Corot mission, but also by Kepler. And from that, we feed the information of the size of the star, the mass, and its age to archaeological studies of the Milky Way. That's yet another topic, yeah, that I cannot go into, but you can get the seismic radius and the luminosity of the star. We have that from the Gaia mission. That's another satellite that's operational right now. So if you have the luminosity, which is the energy output, you know how far away it is. So we can actually transform the oscillation signal that you see here into what we call an astroseismic distance measurement. And if we then compare that to a measured distance by another independent satellite, we see that there is a fantastic agreement. So that means we can actually provide ages and sizes of stars to galactic archaeologists. Okay, let me move on to my pet stars because I have to hurry up, I see. Fast rotators. Now you know how it works for slow rotators. We learned from the sun. We know for successors of the sun, they're all slow rotators. Now we go to this part. Slow waves in fast rotators. And the waves are so slow that they are almost the same period as the rotation. And then you are here. Yeah? Now, do stars do this? Yes, they do. Here I brought one. Huh? We have thousands, but here you see the blue measurements again from Kepler. Overplotted is the Fourier transform in black. And all these peaks are starquakes. To guide your eye, because I suspect you're not familiar looking at this by the day, as I am, you can see a regularity by these red dashed lines, okay? There's a strict regularity that is now in period of the modes. We're at very low frequency, yeah? So each of these quakes take typically half a day. That's 12 hours. If your star rotates at 2 days, let's say, then you better include the Coriolis force, because else you're making a mistake in the force balance, right? And so you see from the patterns that we recognize here that this star actually has all these modes plotted here in black as a regularity pattern. And this slope, this tells me how fast the star rotates. How do I know that? Well, you have your oscillation. Oh, let's take one. And you have your rotation. And so you, as an observer, if the star goes up and down and up and down, the period that you measure is being dragged along, like in my animations, right? And so the frequency of the wave, or its period, is coming faster at you when the wave is going along with the rotation. So you get a shorter period, and we subtract two numbers here, because this is the difference in period between two of these red dashed lines. If you subtract two smaller numbers, then the outcome is a smaller number than if there were no rotation. So each and every of these dots go lower values and to your left. And that's what we call a tilt in the period spacing pattern of the oscillations. And by measuring this tilt, by measuring the slope of this red line, I know immediately how fast the star rotates. This is fantastic. I still find it fantastic by the day, and this is something that the Leuven team is really expert in. This is what we put our efforts in that high rewarding area where nobody else has gone before. That's always nice, right, if you can do something like that. And so here's my famous diagram that I already showed 1.5 years ago. I've added one blue star now, because this is how stars rotate in their interior. We have done this research for these 1,800 stars. As you can see, by now we have about 2,000, which show that young stars are really fast rotators, and then they spin down when they grow old, right? These are all more massive than the sun, yeah? And so from this, we could deduce the way that stars rotate in their interior. And the surprise is, or was, that the inner parts and the outer layers rotate almost in the same way. So that's something that we have learned. And as a conclusion for, let's say, up until the Kavli prize, we knew we had the theory about a factor 100 wrong in terms of internal rotation. Okay. That's good because we have now fixed that in stellar models, right? And so now I thought, let's bring some new things that we didn't know yet. And an exciting discovery is about magnetism, deep inside stars. You know, I've shown that rotation splits up an oscillation frequency into 3 components if it's a dipole mode, right? Here you see that for a star that's a successor of the sun, a red giant. And you see that this split up is not symmetrical. You even see that by eye. Why? Because I have very much blown up the, look, this is below 1 microhertz. This is a tiny shift, but it's asymmetrical. And what causes that? The magnetic field that sits inside this star. Because if you have a Coriolis force or a Lorentz force and they act together, then the split of the frequencies is asymmetrical. So if we detect that, then we have, there is something going on in addition to the Coriolis force. And this is a Lorentz force. So this was discovered by Gang Li and collaborators and Sébastien de Heuvels, who are people in Toulouse, only recently, last year. So this is all exciting because now we can add a third force, right? We have measurements. What's also exciting is that, like, okay, we have now astroseismology for individual stars, but some stars, they live in star clusters. And star clusters were born together, and so we know they are equally old, and they were born from the same chemistry. So that allows us to put much more constraints on the computer models that we are creating. And this is from my postdoc, Dario Fritzewski, who found that in a cluster, this is a color magnitude diagram of a cluster, even for one of these stars, this one, he discovered such modes that are affected by gravity and the Coriolis force, and that means we can age date it. Even one star in the cluster reduces the age uncertainty with an immense factor. So that's what we are now focusing on. even for a more younger cluster like this one. This is one from Gang Li, who is now working in Leuven. That's the same guy who discovered the internal magnetism. He's now moving to cluster seismology, and he has found a beautiful cluster in TESS data that is even younger. So we're gradually shifting to study stars at the younger end of the regime. And the younger end, that means we go gradually up to higher and higher masses. So that's really an exciting field. And here you see 11 pulsators in this cluster. You know the diagrams by now, where you see the oscillations in black, and this red dotted line is in fact a measurement that we have of the internal rotation frequency. And you see that they are intermingled. The rotation frequency and the oscillation frequencies are about the same order. And then you have these gravito-inertial modes. This is something else. I'm 2 slides before the end. Again, Dan Hay is a postdoc in Hawaii, and literally today, just for you, we submitted our paper, where we have combined Gaia astrometry, right, distances, and TESS photometry, discovering 60,000 new pulsators. We have work to do because the scheme that we have been doing so far is star by star. I mean, I need more brains and I need more work power, because as it happens, we were able to show that of all candidate frequencies here in an evolutionary diagram, where we thought, well, Gaia just gives a hint, these are candidates, maybe they're not really true pulsators. What we did is for 100,000 candidates, we went to the TESS data. We have 60,000 confirmed cases. Now, we have to analyze all the TESS data of these stars, and we'll see how it goes. But this is fantastic news. And then we also have binary stars, the tidal force, remember? I can't go into detail, but the higher you go in mass, the more chance you have a companion as a star to live with. And then you have tidal forces and tidal waves. A whole new field by itself that I can't go into except to show you beautiful measurements. Stars do it, right? Binary stars, close binary stars, do show tidal waves. And this is a whole field by itself that allows us to improve and study close binary evolution. Again, I have no time to go into detail, but the basic thing is that if you have tidal waves, they nicely occur at multiples of the orbital frequency. Just like the Earth-Moon system, we know when the tides come, right, at the sea. We know perfectly when. Why? It has to do with the orbit of the Earth around, the Moon around the Earth. Right, here we see exactly at multiples, 0.00 the orbital frequency when the tides are happening. So this is, again, a whole new field. And one of the leaders in this field is Zhao Guo, who has just arrived in Leuven for his postdoc. So I'm very happy with his contribution also to this field. Well, 1.5 years ago, I was treated so well here with the Kavli Prize. You know, at that stage, it was very stressful week in a certain way because I had to do an exam at the European Research Council for a so-called synergy grant to study other effects of fast-rotating stars that nobody has studied yet. I have carefully avoided one force for you, the centrifugal force. This is when stars rotate really fast. Why have I avoided that? Because if you have that force active, your stars get flattened. They are no longer spheres. And so far, all astroseismology is only for spheres. But the fastest rotators are no spheres. They are flattened. And so you see 4 smiling faces here because we did get that grant. So 1 week was both a Kavli Prize and a big grant to study this for the rest of my career. It's a big, long grant, and I'm very happy with that. And real stars are flattened. We can image that in reality. On the observational side, we're building a new machine. You see it here with me in the cleaning room at ESA. This is the PLATO mission. It's a fantastic mission. We're building it. Belgium is heavily involved in this. And I hope to see the data before I retire. That's a promise. And with that, I think I will conclude, and I hope you are convinced that astroseismology really offers a fountain of opportunities. Whatever your topic in astrophysics, somehow I can connect to it. And with that, I thank you for your attention.
I think we have time for 2 questions, if there are any in the audience. Yeah.
How do you determine the spherical harmonic modes?
Sorry, say that again?
How do you determine the spherical
Oh,
harmonic
yes.
modes?
Oh, yeah. That's my pet topic because it was the subject of my PhD. So it's about the identification, how to couple the frequency to the identification of a spherical harmonic. We do that by, statisticians would say, by pattern recognition, right? So we know how to label the modes for the sun, for instance. We know the pattern. And then for other stars, we see if we can recognize the same pattern. Now, we could do this for the sun and for sun-like stars, but there was nothing like that for fast rotators. And so that's why we had to develop this whole new field to recognize that. And so these patterns that I have shown, like these with these red stripes, let's say, the computer cannot follow me. I tend to be too fast sometimes. That's fine. So if you, these patterns, right, they tell me that these are dipole prograde modes. Now, that's because I train myself in the predictions and into looking at how the pattern should look like. And I do that for different spherical harmonics. And then I can recognize it. But it's a totally relevant question. You only can do it if you train your brain. And we use neural networks nowadays to help us. Right.
Time for one more final question, if there are any.
Yeah.
Okay, thank you again for the talk. My question is, let's say you said in the end that the methods that have been used so far are for spherical stars. So in short, how can you distinguish stars to be spherical or not when you can't resolve them?
Ah, yes, very good question. So if a star is flattened, if it's a spheroid instead of a sphere like we have, you can see that in this last graph that I showed here. Some stars are like that, you know. The waves that travel through the star, they feel that it's not a spherical body. You know, their travel time changes. And so, again, this gives frequency shifts. So we have to unravel the frequency shifts from the Coriolis force, from the Lorentz force if it's active, and then on top of that, of the centrifugal force. And each of these forces gives a different shift. So we compute mathematically how it's predicted to shift. And that's how we do things. So again, it's about patterns and deviations from spherical stars would give certain patterns. A flattened star will give another pattern, and we compare these two. But to be honest, we have just started a grant, as you can see here, and I have yet to train myself. So your question is completely relevant. Okay? It's very difficult also for a person like me.
Yeah, we don't have time for more questions, but I just want to thank you again, Conny.
With pleasure. Thank you so much.
For those who've been invited to dinner and has accepted, there will be a